Welcome Science 10 students. This is our velocity time graphs, uniform and non-uniform motion video. It's kind of a long one. There's lots of information, so you may have to view it 10 or 20 times or maybe just a couple times to get it all down. So get ready. The first thing we're talking about is velocity time graphs and what their shape means. So we can look at whether the object is at rest, not moving at all, or moving at constant speed, or speeding up or slowing down. This is all information we can get from the velocity time graph. Our first example here is about an airplane, has a cruising altitude of 10,600 meters and travels at a constant velocity of 900 kilometers an hour east for 5 hours. Now there's a lot of numbers there, but we only need two of them really. We're looking at constant velocity and time for our velocity time graph. So here's our data table again with the time and the velocity and our graph. We can see that Air Canada is going east, our direction is here, for 5 hours. Maybe we're off to Montreal here. But the speed, the velocity, stays the same after every hour. So for 5 hours it is going exactly the same speed. So it's a horizontal line at the top of our graph. This is constant velocity. It is not accelerating. If we wanted to find the slope of the velocity time graph, we can designate east as the positive direction. Usually east and north are positive. The slope is rise over run, if you remember that. The rise is going to be the change in velocity because it is a velocity time graph. So this would be the rise and this would be the run. So we're going to take the final velocity minus the initial velocity divided by the final time minus the initial time. If we go back and look at the graph, we see that the velocity is always the same. So it would be like 900 minus 900, and then the time just changes. But regardless, 0 divided by anything is still 0. So we will know that it has no acceleration, constant velocity. Our units are kilometers per hour squared. Sometimes we see meters per second squared as acceleration. The plane is moving at a constant velocity here, the 900 kilometers an hour, so the acceleration is 0, like we said before. In general, you can recognize acceleration by the units, all of the different variables by the units. We talked about distance, that is meters or kilometers, right? Velocity is meters per second or kilometers per hour. And then acceleration is meters per second squared or hours or kilometers per hour squared. We looked at the slope of the velocity time, the slope of the position time graph, which we did before, or the distance time graph, tells us about the velocity. But the slope of a velocity time graph tells us how quickly velocity is changing or how it's changing, which is acceleration. Here's some different types of velocity time graphs. We're camping, we're by the fire, having marshmallows, and we're not moving anywhere, right? We're just sitting by the fire. So our velocity is constant at 0, but time is going on. So this means it is horizontal because there is no velocity. We could also we wake up and we go canoeing. Why not? We're super active. So in this case, our velocity is not really fast, but it is at a constant speed. So I don't know about you when you canoe, but when I do, I like to just go at a constant velocity at all times. I don't speed up or slow down. I just stay at my, 2 kilometers an hour probably. I think I'm pretty slow canoeing. And as time goes on. So we're not speeding up or slowing down in this example. And then the last one, now I decide to do some sprinting because I'm also a very fast sprinter. So as I'm running here, we start at 0, but we have to take off and go very fast. So I start increasing my speed as time goes on. This shows a positive slope. It means a positive acceleration. I'm speeding up. Sometimes you see non-uniform motion, so it's not going in a straight line. We don't have just one slope. These ones can look a little bit confusing. We have to look at the velocity side and what direction it's going. So in this case, it's going north, which means that anything above this time line is going to be north, and anything below is going to be south. So we still have some acceleration here, but you're going in the southward direction. Then you're just at constant velocity for a while. Then we start accelerating again. Southward, constant velocity. Then we start going northward much quicker. We are speeding up here, right? We are accelerating. We have a positive slope. And then we are horizontal again, which means we're at a constant velocity in the north now. We can also find the area under a velocity time graph. This is displacement. If you remember from one of our first videos, displacement is a vector quantity. You have to look at it from a home base, your position at the start, and where you are from that position. So we also need direction. We have our velocity time graph here. We can figure out the area underneath the graph to tell us the displacement. Doing that, we just use the area formula of length times width. Okay, so we have 300 kilometers per hour east. Oh boy, my writing is messing down here. And then we're going to multiply it by 2 hours, because that took us 2 hours to do. And we get 600 kilometers east, because we are looking for displacement. Now, this square is the next square I'm going to do. I'll use a different color because that's fun. And I have, I'm going to say, what is that, 300 again? Negative 300 kilometers per hour. I see my writing is getting no better. And it's going in a westward direction this time. And then we're going to multiply it by 0.5 of an hour. So, I'll just skip over this line. That looks good. So now we have negative 150 kilometers. I just did that in my head. Can you believe it? And that's west. Oh, I put it there. Okay, good. So if I want to find the total displacement, I would use red because red is good. And I would have 600 kilometers east plus 150 kilometers west. If I assigned their signs, right, positive and negative, to put that together for a total displacement, I always forget to put those, I would have 450, did that in my head again, kilometers east, because it's positive, and there would be my answer. And I found that out from the graph. Totally amazing. So there we go. That's how we can find displacement from a velocity time graph. We can also find acceleration through the slope, which we did with the plane example. What's next? What else could we possibly do here? Well, just another example of velocity time graph, a little more intricate because we have multiple parts in this graph. But we can also find displacement and acceleration from this graph. So here we are. So to find the displacement, we have to find the sum of the three areas. So we have A, and we have B, and we have C, and we've got to add those together for displacement. Okay, so to find acceleration, displacement we did before, so we would just do, the 3 times 4 plus the, what was this, 5 times 1, and then add them all together. But I don't want this video to be too long, so we'll skip to acceleration because we didn't do that yet. No, thank you, Smartboard. So to find acceleration, we're going to find the slope of each section. So here's our graph again, so we don't forget, and here's region A. So the velocity here is at a straight 3 meters per second, at 0 all the way to 4. Yes. So I know that it is 3 meters per second minus 3 meters per second. It's constant velocity, right? Then I have 4 minutes. Well, I have to convert that to seconds. So if I have 4 minutes, I know that for every 60 seconds is 1 minute. This kind of looks like unit analysis from chemistry. Remember when I told you it would be useful? And then we just multiply those babies together and we get the 240 seconds. However, because we're doing 3 minus 3, it's going to be 0. We know that the slope of this line is 0. We have no acceleration, positive or negative. Now B is a little bit different. We do have a slope here. We're going to find the rise over run, the change in velocity. Oh, my pen's a little bit off. 1 meter per second to 3 meters per second as its initial velocity. Divided by 60 seconds, and we get 0.033 meters per second squared west because we are going down. So east would be upwards. And then C again is a horizontal line, so its slope is also 0. So we could find acceleration that way. To calculate the average velocity on a velocity time graph, you can determine the area under your velocity time graph and divide it by the total time. Or if you have different displacements over different time intervals, like our last one, you can add the total displacements together and then divide by the total time. All right, so here's another example. We want to find the average velocity of a student who jogs 750 meters east in 5 minutes, then does static stretches, so it's not moving, for 10 minutes, and then runs another 3 kilometers east in 30 minutes. Oh man, this is a lot of stuff we're going to have to do. So the first one, we got to find the displacement values. So I'm going to add them up, right? I have to find the total displacement. I ran 750 meters, and then I stayed in one spot. I'm imagining I'm the student now, I guess at this point I jumped to that. And then 3,000 meters. Where did 3,000 meters come from? Let's go back and see. Oh, it's 3 kilometers. Now, when we have to do conversions that way, if you remember, we use my handy saying of killer hens defeat modern day chicken men. And because I was in kilometers, I have to go to meters. I go 1, 2, 3. So I had 3 kilometers, right? And then my decimal is here. It's getting over 3 spots. 1, 2, 3. I fill those with zeros. Sometimes it gets messy, but I don't mind. And that's where I got the 3,000 meters from. Okay, so if I add those together, I will find that I have gone 3,750 meters. I then have to add the time intervals and convert them to seconds. So I'm going to add all the minutes up, 5 minutes, 10 minutes, 30 minutes, to get a total of 45 minutes. And then I have 60 seconds in each minute. Remember I did this on the last one. It looks the same, kind of like unit analysis in chemistry. Multiply those together and get 2,700 seconds. To find the average velocity, I'm going to use total displacement over total time. Slot in my numbers, the 3,750 over 2,700, and found that I have gone 1.4 meters per second. So beautiful, and that is my answer in a positive direction. Oh, here's another one of a bird. So we have to describe its motion in the velocity time graph in this figure that's beside us here. So we could decide whether the acceleration is positive, negative, or 0, and when the bird changes direction. Probably the bird looks something like this. This is a very important part. I am extremely good at drawing birds. I'm not sure what that's on his head, but I kind of felt like he needed it. There we go. So draw that in your notes so you remember the bird. And we'll go next. Okay, so here is the graph again of our bird. And we're going to look at acceleration, which is the slope. So the first part of A is here. And we notice, remember, this is north. It's hard to see. So this is north, and this is going south. So in the first part, our acceleration is negative because the final velocity is more than its initial velocity. It's also speeding up in the southern direction. So the slope is negative, and the bird's acceleration is negative. Then at B. B is, again, this horizontal line. We know about this, right? This means that it's 0. There's no acceleration because the slope is 0. There's no slope. It's horizontal line, no acceleration. C. Well, C looks an awful lot like A, so I'm going to guess negative again, as it's going in the southern direction, and you have final velocity more than initial velocity. D, oh, this is getting too easy here. D is, again, another horizontal line. We know about that. That's going to be 0. Oh, look, I got some kind of crazy thing here. It's going to be 0. And then E is going way up this way. So this is going to be positive. I'll just get rid of that. It's not really helping us out anymore, is it? Okay, so where are we? D, E? I get confused. E is positive, so final velocity is positive because the bird is now flying north. The slope of the line is positive. The acceleration is positive. And then F again, horizontal line, look way up there. It is 0 velocity. No acceleration, not 0 velocity. Constant velocity, no acceleration. And the last question it asked was about when does the bird change direction? changes direction right here at 8.5 when it crosses the timeline from south to north. Slope of a velocity time graph. We've done this before already, right? Rise over run. Look at this fancy thing I did. I learned how to do this. So we have the rise, which is the change in velocity, and the run, which is the change in time. We make it look fancy like that, so we seem really smart. Then we take the numbers. So we have 10. Well, this graph doesn't match this at all. So let's imagine the graph looked different than this, where we had maybe the final velocity is 10, like way up here. Oh, this is acceleration graph. I see. So 10 meters per second minus the 4 meters per second. Oops, put down the pen. And then the change in time. So we can get a final answer of 4 meters per second squared. That graph does not match this question at all, so ignore that. In summary, I'm sure you're very happy to know I'm finished talking to you. The velocity time graphs are very useful. They can give you all kinds of things, like I said right at the beginning, and I didn't lie. So a velocity time graph can give you instantaneous velocity. You could just look at it at one specific point and say that's how fast you're going. You can calculate the slope to figure out acceleration. Is it positive? Is it negative? Is it zero? We just did that with the bird. And the area under the velocity time graph will give you the object's displacement. Where is it? And we did that one too with that previous question. We can also determine the average velocity of an object over the time interval. So total displacement over total time. Now you know all these things and you are going to show them to me tomorrow. Good luck.